So we discussed in the last video how the colligative property of vapor pressure lowering results in the vapor pressure of a solution being less than the vapor pressure of a pure solvent because of the interactions between the solute and the solvent. Well, one of the other results of this interaction and this lowering of the vapor pressure is that it actually has an effect on the boiling point and the melting point of the solution versus the pure solvent. Because if you remember, those things are related. Especially the boiling point is related to the vapor pressure, as that is the whole definition of the boiling point is when the vapor pressure is equal to the atmospheric pressure. And so if you're messing with that vapor pressure, you're going to mess with the boiling point as well. Specifically, what happens with these two phase changes is when you have a solution, the vapor pressure lowering is going to, and just that interaction in general between the solvent and the solute is going to cause the liquid phase to expand. So the liquid phase is going to occur over a larger pressure and temperature range than it was before. Another way of saying this is that the boiling point will increase. You will have a boiling point elevation, and you will have a freezing point depression. If you have a hard time remembering which one goes up and which one goes down, which one is elevated, which one is depressed, the easiest way I know to remember it is that the one that is higher goes higher, and the one that is lower goes lower. They don't work opposite in that sense. The total area in which the liquid exists increases. So you go to higher temperatures on the high end and lower temperatures on the lower end. This is why we use a solution of antifreeze that is 50-50 ethylene glycol and water, because we want to have that lower freezing point, but we also want it to be able to go to higher temperatures before it turns into a gas as well, because the liquid is what is useful for carrying away heat, and solids and gases not so much. Gases just because they don't diffuse heat very well in the first place, and solids are not very useful because, well, then you essentially, it's like you're pouring marbles into your car. It's like not terribly useful, clogging up the pipes there. You want it to be liquid. So the melting point depresses, freezing point elevates. The equations that quantify how much these change are actually practically identical to one another. So the boiling point is going to change based on this equation here. So it's the delta T sub B is the change in the temperature of the boiling point. That is equal to what we call the molal boiling elevation constant, or boiling point elevation constant, times the molality of the solution. So the change in the temperature of that boiling point is just a constant times the molality. Now that constant is going to be different for every different material, so you will have to look that up if that's not what you're trying to find in the first place with those solutions. The freezing point, on the other hand, and I have a typo here on this slide that should say, instead of boiling elevation, it should say freezing depression. Just when I made these slides, because the equations are exactly the same, I just copied and pasted and forgot to change that. So the freezing point depression is just the constant times the molality as well. So they are exactly the same as one another. And actually, boy, there's several typos on this slide here, because those examples are from an old book that we no longer use. But we will have some examples from our current book in just a second, I believe. So these equations are pretty straightforward. They're pretty simple. They're very simple. It's just this is equal to this times that. In terms of the algebra, you can't really get much more simple than that. The tricky point comes into actually solving for those individual parts. So if you need to find the molality, for example, that might be a little bit tricky given just depending on what you're given in the question. So let's look at one of those examples here. We're asked to calculate the boiling point of a 3 molal solution of a non-volatile solute in benzene. Now to do this, we will need the molal, let's see, we're looking for the boiling point, so the molal boiling elevation constant, which I don't think I have here. So let me, yeah, I don't have my book nearby where I can get that either. So we're going to have to look that up. So let's see here. We are just going to go down here. And we want colligative properties. Scroll, scroll, scroll. Okay, here we go. So the boiling elevation constant for benzene is 2.53 degrees C per molal. Okay, so now that we have the constant there, 2.53 degrees C per molal, we should be able to solve this equation, or solve this problem here. So our general pathway is going to be, we need to use the molality of the solution, which is given to us in the problem, as well as the constant, to find the change in the boiling point, and then using the change in the boiling point and the original boiling point, we can find the new boiling point. So delta T is going to be the constant, 2.53 degrees C per molal. The molality is 3. And so this is going to be something around 7.5. So 7.59 degrees C is the change in the boiling point. And this is because the molals cancel out, leaving us with just degrees C. And the freezing point of benzene, I again do not remember off the top of my head. So if we go back and check that again real quickly, that is 80.1. So we have 80.1 is the original boiling point. The change is 7.59. And so because this is the boiling point that we're looking at, it is going to be elevated. So the new one is going to be 80.1 plus 7.59. So that is 87.69 degrees C. All right. So that is our new boiling point. Let's look at just one more here, I think. Yeah. So one more example here from the book. It says, find the boiling point of a solution of 92.1 grams of iodine in 800 grams of chloroform, assuming that the iodine is non-volatile and that the solution is ideal. That little bit there at the end about the solution being ideal, that just means that we can use the equation. Because we're doing the fairly simplified version of this. There are certain situations where you have non-ideal solutions, mainly when the solute is when the solute is volatile, that would be a non-ideal solution. We're assuming that it's non-volatile, so it is ideal. Okay, so once again, it's the boiling point. Although if it was the freezing point, again, it would just be the exact same equation. We would just have to look up a different constant. So we have the change in the boiling point is equal to the constant times the molality. In this case, we're not given the molality directly. And so we can go ahead and look up the let's see, so we have 3.63 and 61.26. So 61.26 degrees C. That was the original boiling point of chloroform, and then 3.63 degrees C per molal was the constant. So we have this. We just need to find the molality. So actually, why don't you go ahead and try to find the molality for this on your own. So you have what you need there on the screen. You have your original boiling point. You have the amount of everything in the solution. So why don't you go ahead and try to solve the rest of the question there and find the new boiling point of the solution. So go ahead and pause the video and give that a try. Okay. So like I was hinting at there, the first thing you should do is try to find the molality. So if you remember, the molality is the moles per kilogram of the solvent. And I think actually there's a, it's marked out here, but I'm going to go ahead and make that go away for a second just so we can see what I already have written. The iodine is our solute, so that's what we need to figure out how many moles. It's the thing we need to determine the moles of. And the kilograms of solvent, that's going to be pretty straightforward because we're given the grams of the solvent. And so this kilograms of solvent is just going to be 0.8, since the chloroform is our solvent. So iodine is I2. If I remember correctly, iodine is 55? No, sorry, 53 was the atomic number. So the molar mass of iodine is 126.9, and we have two of them. So that is going to be 253.8 is the molar mass. So if we go ahead and take the 92.1 and divide it by that number to get the number of moles, that would be 0.363 essentially moles of iodine. And so if we go ahead and do that other calculation here, divide the 0.363 by the number of kilograms of solvent, that gives us 0.4536, we'll say. We'll worry about the sig figs at the end. For now, we'll just go with that. Molal. Okay. So now we have the molality of our solution, and we already have the constant. So the change in the boiling point is going to be 3.63 degrees C per molal times 0.453 molal. So that is essentially 1.65 degrees C. And so then, once again, because this is a boiling point, it is going to elevate from the original boiling point. And so our new boiling point will be 61.26 plus 1.65. And so that is 62.9 degrees C. Is our new boiling point. Alright. I think we'll call it there for this video. Like I said, there's a little walkthrough there of how we just did that. That's just describing what we just did. In the next video, we'll have a very short one, just briefly talking about osmosis and colloids. So we'll see you in the next and last video for this chapter.